Fusion and fission are two different types of nuclear reactions used to produce nuclear energy. Here are the main differences between fusion and fission. Fusion is a nuclear reaction in which two light nuclei combine to form a heavier nucleus. It usually occurs in high temperature and pressure environments, for example, in the sun and in hydrogen bombs. Fission is a nuclear reaction in which a heavy nucleus breaks apart to form smaller nuclei. This reaction usually occurs under neutron bombardment and is used in nuclear reactors or the detonation of nuclear weapons. Fusion reactions usually release large amounts of energy. The Sun is a star that produces energy through fusion reactions. Fission reactions also release energy, but generally produce less energy than fusion reactions. Fusion is an energy source used in hydrogen bombs. However, practical applications for energy production under control have not yet been realized. Fission is used in nuclear reactors to produce electrical energy and in nuclear weapons technologies. Fusion reactions usually occur between light nuclei, for example, hydrogen isotopes. Fission reactions usually occur between heavy nuclei, for example, isotopes such as uranium-235 or plutonium-239. These fundamental differences illustrate the main distinctions between the nature and applications of fusion and fission. Fusion reactions in the world can be created under laboratory conditions, but these reactions generally require large energy input and cannot yet be carried out on a scale that can be used for energy production. There are two main types of fusion reactions: thermonuclear fusion and magnetic fusion. Thermonuclear fusion, temperature-controlled fusion. This type of fusion is performed in high-temperature plasma environments. This plasma usually contains deuterium and tritium, which are hydrogen isotopes. This reaction requires an environment that can sustain high temperatures and pressures. To date, several different thermonuclear fusion experiments have been conducted around the world. For example, the ITER, International Thermonuclear Experimental Reactor, project is an international effort aimed at building a temperature-controlled fusion reactor. Magnetic fusion, tokamak. This approach is based on keeping and controlling the plasma using magnetic fields. Tokamaks are devices that trap plasma through magnetic fields. The ITER project aims to create a temperature-controlled fusion reactor in the tokamak style. The main goals achieved in these experiments are to keep fusion reactions under control, to reach sufficient temperature and pressure, to maintain energy balance, and to continue the reaction. However, currently obtaining energy from such reactions requires overcoming several technical and engineering challenges, and studies in this field are ongoing. Sustaining efforts to capture fusion energy faces a number of technical and engineering challenges. Here are a few strategies and suggestions to overcome these challenges. High temperature and pressure. Maintaining high temperatures. It is difficult to maintain the high temperatures required for fusion reactions. Developing new materials and cooling technologies is important to control temperature and reduce energy losses. Sustaining high pressures. Fusion reactions often require high pressures. Magnetic fields or other types of controls can be used to increase plasma stability and minimize energy losses. Energy balance. Achieving energy balance. In order to obtain more energy from fusion reactions, the reaction must be kept under control and the energy output must exceed the input. This includes resolving technical challenges in energy balancing. Materials engineering. Durable materials. It is important to develop durable materials that will be exposed to high temperatures and radiation. These materials ensure the long life of the reactor components. Magnetic control. Enhancement of magnetic fields. Magnetic fields are used to control plasma. In order for magnetic fields to be more effective and powerful, new magnet designs and materials need to be developed. Innovation and collaboration. International cooperation. International cooperation in fusion energy research should be increased. Joint efforts on large-scale projects allow pooling of resources and faster progress. These recommendations are general strategies for overcoming technical and engineering challenges in fusion energy research. However, work in this area is ongoing and it may take time to fully resolve these challenges. Is there any material or product that is resistant to high temperature, pressure and radiation to be used for fusion reactions? Although studies on high-temperature and pressure-resistant materials that can be used for fusion reactions continue, developments in this field are not yet fully mature. However, some materials and design strategies are being considered for potential use in fusion reactors. Here are some of these materials and approaches. Tungsten is a metal known for its durability in high-temperature and radiation environments. It is recommended for use at plasma contact points in fusion reactors. Some ceramic materials are resistant to high temperatures and radiation. For example, beryllium and lithium ceramics are being evaluated for use in fusion reactors. Graphite is a material that performs well in high-temperature environments. It can be considered for the walls of the plasma chamber and some structural elements in fusion reactors. Superconducting magnets used to provide magnetic control can help minimize energy losses. It is important to develop effective materials that will capture tritium and deuterium, which are the fuels required for fusion reactions. These materials and design strategies are being investigated to increase the durability of fusion reactors. However, as work in this area is still in the experimental stage, further research and development is required to evaluate feasibility and efficiency.